Hello, this is a review session for physics midterm. A lot of topics we're going to go over, mostly on probably the first and the last pages of the reference table, dealing with mechanics, not necessarily in the same order that we did them in class. We're going to go through them pretty quickly. Please refer to your unit packets as well as you study for this. We're going to start with measurement. And so there's certain things you need to know about measurement. Starting with units, really important that you need to know the units that go with different things. For example, if you see kilograms, that is mass. Newtons is going to be force. Momentum and impulse can be in multiple units. You're going to see them either in kilograms meters per second, or you might see newtons times seconds. And if you look at the equations, they can often help you out. Momentum being mass times velocity, impulse being the change in mass times velocity, but also is force times time. So force times time, newtons times seconds, mass times velocity, kilograms times meters per second. You might see newtons and force and realize that you need to know that force can be expressed as ma, mass times acceleration. So a newton is the same thing as a kilogram, which is mass, and meter per second squared, which is acceleration. So acceleration is meters per second squared. Velocity is in meters per second, as is speed, distance, and displacement, and position are all in meters, etc., etc. You really need to know units, even things like the universal gravitational constant, newtons times meters squared per kilogram squared. You got to know that. You don't have to memorize that, but that is on the reference table. Whenever you're asked to do an equation, show all work, including equation and substitution with units, you need to include the equation net force equals mass times acceleration. Then you've got to put the right units in. 2 kilograms times 5 meters per second squared. And write your solution. You don't have to use units in the middle, 2 times 5, and you can just say 10, and the correct units with it. Newtons is the correct unit. You could write kilograms, meters per second squared, that's fine too. If you want to, I would strongly encourage you to actually. Write m equals 2 kilograms, a equals 5 meters per second squared over on the side. Then if you do the substitution and if you leave something out, we can still give you full credit for it. You do need to know scientific notation as well. So scientific notation, things like 10 to the negative 1 equals 0.1, 10 to the 0 equals 1, 10 to the first equals 10, 10 to the second equals 100, etc., etc. And then translate those into objects, like the width of a door might be about 1 meter. So what is that in other forms of units? Well, 1 meter is equal to 100 centimeters, right? It's equal to 10 to negative 3 kilometers. It's equal 10 to the 3 meters. So you could say, well, 1 meter is equal to 10 to the second centimeters, or 10 to the negative 3 kilometers, etc., etc. If you're not sure about any of the powers, the prefixes, you'll see things here: tera, giga, mega, kilo, deci, centi, etc., etc. Most common ones that we're going to transfer from would be kilos, it's just 10 to the third, or centis, which is 10 to the negative 2. Centimeters to meters, right? If you go to centimeters to meters, you just divide by 10 to the negative 10. So let's say, for example, 2 meters, you want to go to centimeters. You can use dimensional analysis. You want to get rid of the centimeters, you'd go to meters. 1 meter in and you can say, well, centi is 10 to the negative 2, so that's 10 to the negative 2 meters equals 1 centimeter. And then you go 2, the units end up canceling out, divided by 10 to the negative 2, so 2 meters, 2 divided by 10 to the negative 2 is 200. You can do that. You could also do 2 meters, realizing that 1 meter is 100 centimeters. Same thing as we had before, just different ways of expressing it, and you end up getting 200 centimeters. And vice versa. Grams to kilograms. 200 grams is equal to a certain number of kilograms, kg. Well, 1 kilogram is equal to 10 to the third grams. So you end up with 200 over 10 to the third, which is 0.2 kilograms. If you're not sure how to do this, remember that E button. You could do 200 divided by 10, divided by 1e3, not 10e3. 10e3 would be 10 times 10 to the third. This is 1 times 10 to the third, 1e3, and you'll get that same number, 0.2 kilograms. You're going to want to do the same. Know that 1 Newton is about, the weight. Newton's is force. Weight is the force of gravity. Is about the weight of an apple, or a calculator, or a golf ball. If you want to do mass, you can convert mass to weight pretty easy. M equals F sub g over g, which is just a change in this equation right here. So if something is, for example, a golf ball is about, say, 1 Newton, and you want to change that to kilograms or something like that, well, you can say 1 Newton divided by 9.8 meters per second squared. It's about 1/10, about 0.1, so it's 0.1 kilograms, which is going to equal 10 to the second grams if you changed it like that, because we know that a kilogram, 1 kilogram, is 1,000 grams. Cancel those out. 0.1 times 1,000 is 100, which is 10 to the second. Okay, let's talk about vectors. So vectors are used to express a measurement that includes both the size of something, which is known as the magnitude. See, that word magnitude just means size, and the direction. So only certain kinds of measurements use vectors. We call these vector quantities. And you should memorize this. Things like force has a size and a direction to it. Acceleration has a size and a direction to it. Velocity has a size and a direction to it. Displacement has a size and a direction. Impulse, momentum, weight is a good one you might be fooled about. Vector quantities. Now we also have scalar quantities, and scalars don't have a direction. They only have a magnitude. So, for example, velocity is often paired up with speed. Vector, v, velocity, v. Scalar, s, speed, s. Both are measured in meters per second. Your speedometer doesn't tell you your direction. If you had a velocimeter, it would tell you the direction you were going in, 30 meters per second east, for example. Displacement, which is your change in position. That change has an angle or a direction associated with it. This is different than distance. Distance would be just, for example, how far total you go. There's several other vectors. They're not necessarily paired up as evenly with, several other scalars not necessarily paired up as evenly with these, but you see things like mass is a scalar, energy, work, power, charge, for example, current. A lot of different scalars that we're going to use, or we have used in the future. We'll see more later on. Impulse is a vector that it always is in the same direction as your net force. Momentum is always in the same direction as your velocity. Acceleration is always in the same direction as net force also, F net. Weight, F sub g, That's the force of gravity. And so that always points to the center of the Earth, or whatever objects you're talking about. Question mark. So if you have two gravitational objects, that would point towards the center of them. Okay, now vectors continued. We will often express with arrows. So this could be your force vector. Maybe we have an angle. Let's say that theta is 30 degrees north of east. Meaning we'll go east, we look up, and we measure to the north 30 degrees. You could measure this, and you may have to measure this with a protractor. This is not measured. We might have a scale, for example. The scale with these is going to be, 1 centimeter equals something, right? Let's say 1 centimeter equals 10 newtons. So this is a force vector. And so I could be like, oh, let's measure this out. So let's say that this is 5 centimeters, and we know that 10 newtons is 1 centimeter. So just dimensional analysis this. So 5 times 10, that's going to be 50 newtons of force at 30 degrees north of east. And so it's pretty common to express these force vectors in terms of angles. Now, we will sometimes look for vector components. So let's say this is your force vector. Well, we could express this vector in terms of a combination of other vectors. And we know using vector addition, we're going to add tip to tail. You really need to know this. You're going to see it. I promise you. You're going to see it at some point. So adding tip to tail means, let's say we add vector A and vector B. Well, we've got to add them such that when one vector ends, the next one begins. So you could do it like this and say, hey, B, I can move vectors. I just can't change the angle. So A plus B going northeast and then going east gets me out here. So my resultant would be this. You might see A plus B already drawn that way. It still gets you a resultant out there. You might see A and B drawn separately. You could draw them like this, and you could draw them like this. A and B. Still adding the tip to tail method. You're still going northeast and then east with your forces. And they're going to result in a force that is northeast and is longer. So this is your resultant right there. So this is why with force components we can say, hey, okay, let's make a right angle triangle is usually what we end up doing. So F sub y and F sub x. And what we find is that the cool thing about this is that vector force is equal to the addition of F sub x plus F sub y. So anytime we're dealing with force F, we can instead deal with the components F sub x and F sub y because they are equivalent to the same thing. They're just in separate directions. And the reason we do this is that sometimes it's more convenient to deal with separate dimensions. For example, gravity is a vertical force, so it only acts in the y direction. It does not act in the x direction, so we can separate those to be more convenient. Okay. Something that you might see too is the equilibrant, and that is the vector that restores equilibrium. And this is a force vector right there. So if that is your force A and your force B, to get to equilibrium, that means your net force is 0. So that means that your equilibrium E has to go backwards in the opposite direction. It is essentially the opposite of the resultant. So your resultant would look like that. Your equilibrium is in the opposite direction. Okay, as we continue, let's move on from vectors. We're going to continue to see vectors. Don't forget, by the way, the Pythagorean theorem, and you'll see some of this here. This works with the vectors A sub x, A sub y. This is vector A, so this is the component thing. This is your angle theta, so you'll see an equation here. A sub y equals A sine theta, A sub x equals A cosine theta, and then You probably don't need that as long as you know trig. So you can go to page 5 and look at the right angle trigonometry thing here. It's about the only time you're going to need to go into the middle of the reference table for this first midterm, where you see a right angle triangle and some equations for things like circumference and angle. SOHCAHTOA, sine is adjacent over cosine. Cosine is, sine is opposite over hypotenuse. What am I saying? Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And you'll see force components like this, like you apply a force, right? Well, what is the vertical and the horizontal, or what is the x and the y? And so if that's your angle theta there, this would be f cosine theta, because it's adjacent. That'd be f sine theta. So we find that, let's just make believe this is a 3, 4, 5 triangle. 3 newtons, 4 newtons, 5 newtons. So the total force might be 5 newtons. That 5 newtons is made up of a component that's 3 newtons and a component that's 4 newtons. Or you could just simply have separate forces, and you can say, I have a 4 Newton force and I have a 3 Newton force. What's the total force? The total force is 5 newtons. So what is this a sign of? Well, we are not dealing with scalar addition. What we're seeing is that a 3 Newton vector plus a 4 Newton vector, in this case, equals a 5 Newton vector. So it's not 3 plus 4 equals 7. If you had a 3 Newton vector and a 4 Newton vector in the same direction, meaning there was 0 degree difference, then they would add up to be 7 newtons. If you had a 3 Newton vector and a 4 Newton vector in the opposite direction, meaning 180 degree difference, then they would add up to be a resultant of 1 Newton. Or in this case, the 3, 4, 5, they end up being a 5 Newton vector. So what we find is that the total sum of these can be anywhere between 1 and 7 newtons. So the difference will give us the minimum, the sum will give us the maximum between 7 and 1 if we don't know the angle. If we know the angle, we can use SOHCAHTOA and stuff to figure that out. Let's go on to motion. We're not going to start with forces here. We've started with physical descriptions of motion, and we're going to look at the kinematics equation. So you see V equals d over t. Keep in mind, this is average velocity. Average velocity, meaning if you start at 0 meters per second and you end up at 20 meters per second, your average is 0 plus 20 divided by 2, 10 meters per second. So if it takes you 2 seconds to go from 0 to 20, your distance traveled would be average velocity times time. So that would be 10 meters per second times 2 seconds, that's 20 meters, right? Keep in mind, we're not using the final velocity, we got to use the average velocity. If you don't want to use the average velocity, that's totally fine. You've got other kinematics equations here. A equals delta V over T, where delta V is V final minus V initial over time. Let's say you go from, let's say your acceleration is 2 meters per second, right? And you start at 10 meters per second, and that should be 2 meters per second squared, because that's meters per second per second. So every second you're increasing your speed by 10 meters a second. So time equals 0, your velocity is going to be 10. Time equals 1, your velocity is going to be 12. Time equals 2, 14. 3, 16. So every second it goes up by 1. You could have a negative velocity as well. That's totally fine. It just means your speed is decreasing. Other kinematics equations, V final equals V initial plus AT. You got D equals VI
This is a reminder that the safety meeting will begin.
Okay. D equals VIT, initial velocity times time, plus 1/2 AT squared. And V final squared equals V initial squared plus 2AD. So whenever you're doing these questions, I recommend saying, hey, let's make a table. Distance is, initial velocity is, final velocity is, acceleration is, time is. And typically, not always, but usually you need 3 of these to find the 4th. And there's one that you don't need. So if you don't have time, ignore this equation. If you don't have time, use this equation because it doesn't have time in it. If you don't have final velocity, you can use this equation, for example. If you don't have distance, you can use this equation. So once you get 3 of the variables, you can find the others. Keep in mind that these are vector quantities, acceleration at least, and velocity and displacement are. I call that distance, it's really displacement. So everything except time is a vector quantity, which means they all have directions. And we use those directions, positive or negative signs, to indicate direction. And usually to the right is positive and the left is negative. Usually up is positive and the down is negative. But you are more than welcome to change those if you like, as long as you are consistent about them. We also see some things with motion, like if acceleration and velocity are the same sign, could be both positive, could be both negative, you're going to be speeding up. If you see acceleration and velocity are opposite signs, one's positive and one's negative, you're going to be slowing down. So if you look at dot diagrams, for example, that look like this, could be a car that's going to the right and slowing down, or it could be a car going to the left and speeding up. Hopefully they would tell you the velocity, because the velocity indicates the direction of movement. But if it's going to the right and slowing down, that tells you your acceleration is to the left, right? If it's going to the left and speeding up, it's telling your acceleration is to the left. So both of these diagrams have an acceleration to the left, but they describe different objects. And unless you know the velocity, you can't tell. And in fact, oftentimes you might know what the acceleration is doing without knowing what the velocity is doing. Like an object that is a projectile. If I tell you it's a projectile, you know its acceleration is negative 9.8 meters per second squared vertically, but you don't know what it's doing in terms of actual motion. Now, it always helps to divide these things into 2 categories: constant speed / or not moving. Keywords that you see versus an accelerated motion. So if your speed is constant, that means your acceleration is 0 meters per second squared. And there's a big asterisk, because technically, I mean constant velocity. So unless you're in circular motion, and when circular motion, your velocity direction changes. Even if your speed doesn't, your direction of motion is changing. And if your direction changes, then you're accelerating. So your acceleration is always going to be 0. Now, if you're accelerating, your acceleration is not 0. And if it's not 0, you got to use your kinematic stuff. But if it is 0, if you're moving at a constant speed, or you're not moving, well, then you can simply say, hey, your velocity average is just your velocity, right? So you get d equals vt. Or similarly, if you used the equation d equals vit plus 1/2 at squared, but the 1/2 at squared goes away because your acceleration goes away, d equals vt. So you can simply use d equals vt with constant speed stuff, but not when you're dealing with acceleration. Now let's talk about what happens when we add force. So force, I'm going to leave this here for a second. So I'm going to add forces to motion. And we saw the couple of laws. The first law, which says an object in motion stays at a constant speed in the same direction forever, unless there's an unbalanced or a net force. And this is true for objects at rest. An object at rest isn't moving, so will stay at rest forever unless there's a net force. And the net force is just the sum of all forces. And we'll talk more about that later. The first law is sometimes called the law of inertia, and which is to say objects with more inertia have a harder time of changing their speed or direction of motion. And when you see inertia, just cross it out and write mass, because they mean the same thing, which gets to Newton's second law. Net force is mass times acceleration. So we are now on the second law. On the reference table, it's written as acceleration is net force over mass. So an object with less mass will have a bigger acceleration than an object with more mass if they have the same net force acting on them. So let's go back to the constant speed acceleration thing. So if your forces are, this is often called balanced forces or an equilibrium, versus acceleration where you're going to use and if it's balanced, your net force is 0, versus acceleration, which would be unbalanced and not in equilibrium. Now note, you can have a situation where it is balanced in one dimension and not in the other. Like it can be balanced vertically but not, well, usually it's balanced horizontally but not vertically, etc., etc. We're going to see that quite a bit coming up. Okay, forces. Now we often will express forces as, take this away. We'll often express forces using free body diagrams or force diagrams. And they are drawn to scale, starting at the dot, or sometimes the edge of the box. So let's look at this right here. Boom. Let's say we got a force to the right and a force to the left. 5 newtons, 2 newtons. The net force, or the total force, is just 3 to the right. How about this? 5 newtons, 2 newtons, 2 newtons. Well, the 2 newton up cancels the 2 newton down, so your net force is simply 5 newtons to the right. Now there's different ways to get this sort of situation. Imagine this. You could have a box on a surface and you apply a force of 5 newtons to the right. Well, then you're going to accelerate to the right. Your acceleration is going to be net force over mass to the right, because acceleration and net force are always in the same direction. So this kind of object could be, you know, moving right and speeding up, or, because I didn't tell you what the velocity is, it could actually be like moving left and slowing down. So imagine you slide a box to the left. It could have a weight down of 2 newtons and a normal force up of 2 newtons, and well, you're not going to have a 5 newton frictional force, so numbers aren't realistic. But something could be moving to the left and slowing down, like it could be sliding to a stop, and you'd have a 5 newton force to the right. So that is entirely possible. Different ways to achieve these. Let's say you got a free body diagram. We'll continue with FBDs, right? Free body diagram that is like this. 7, 3 newtons, 2 newtons, 5 newtons. Well, it gets complicated if you want to do this all at the same time, but let's break it into components. So this is your free body diagram, but it simplifies. Simplify it. 7 right minus 3 left gives me 4 to the right. 5 up and 2 down gives me 3 newtons up. So this gives us something like this. 3 newtons, 4 newtons, which if you complete the parallelogram or add them as vectors, I'm going to move that there because we need to add tip to tail. This would be your net force, which is your resultant. And that net force, if you look at it, we've now got a 3, 4, 5 triangle. So the net force is going to be 5 newtons using the Pythagorean theorem, because 5 squared equals 4 squared plus 3 squared. Let's talk about some different types of forces. You might say an applied force. which is just a push or a pull. You might say the force of gravity, which is AKA the weight of an object. So don't get confused between weight and mass. You might say tension is a kind of force that involves ropes or strings, which can only pull, they cannot push. You could say F sub n is equal to your normal force, which is perpendicular, that's a perpendicular sign, to a flat surface. So if you have a box sitting on a surface, it's got a weight down, but the thing that keeps it from falling down is a normal force up, meaning the table pushes on the box. And oftentimes, because it's going to be balanced, you'll know that F sub n is equal to F sub g, except it's just up in this case. Not always true, but often true. You could have a normal force situation that looked a little bit like this, right? You could have something that you're pushing against the wall. Well, if you're pushing against the wall is going to push back. So that would be your normal force, and that might be your applied force. And they're probably equal and opposite, because you cannot push it into the wall very easily. Not probably pushing it through the wall. Maybe this is a book, so you could have a normal force down, and you would have a frictional force up. A frictional force, you got to have something that's keeping it up, right? Because it's not the applied force. The applied force is horizontal. So apparently you're pushing it hard enough that it has a big enough normal force to get a frictional force that can keep it up. I'm going to talk more about some of these in a little bit, but let's talk right now about weight, which is F sub g, force of gravity. And we can say this is equal to mg. You really, really, really need to know this. You should know this by now. You can also write it as g equals F sub g over m, and that is the equation that you will see here, g equals F sub g over m. And you'll notice this is similar to net force is equal to ma, but they're different. We got to be really clear, because a is your actual acceleration. And some things like your weight doesn't change as you accelerate. It's just how much the Earth pulls on you. Unless you're going to such extreme distances that we start using the other gravitational force equation, your weight's not really changing. And g is just a constant, which is equal to 9.8 meters per second squared on Earth. Different on other planets. And that constant represents the acceleration due to gravity. Meaning if you were to drop an object or throw